When a thick steel hook strikes a fish's jaw, pulling harder doesn't guarantee a catch. Often, the metal simply flexes and fails to penetrate. That happens because a fish's jaw isn't made of simple, static bone. It is a dynamic, highly evolved biological armor, and thanks to a property called strain rate sensitivity, this tissue actually becomes more resistant to puncture the faster you strike it. This X-ray micro-CT scan of scale cross-sections shows that multi-layered defense mechanism at work. The outer layers contain microscopic calcified plates called tesserae. When struck, the internal plies underneath delaminate and stretch, absorbing and dissipating the sudden mechanical stress. If you try to overwhelm this layered defense with sheer physical strength, the kinetic energy has nowhere to go. The metal either bounces off the slick outer layer, or it buckles and snaps under its own load. Overcoming this defense requires mastering the variables of the pressure equation. Pressure equals force divided by area. Let's isolate the A in that equation. This represents the microscopic surface area at the very tip of the hook's point. Traditional hooks are sharpened mechanically, essentially ground down by a metal file. This physical friction leaves microscopic fissures and a blunter, wider surface area struggling to pierce tissue. To eliminate those imperfections, manufacturers use a chemical sharpening process. After forging, the hook is dipped into an acid bath. The acid eats away the outer edges, forging an ultra-thin, perfectly smooth micropoint. The math here is highly sensitive. As that surface area approaches zero, the localized pressure applied to the biological tissues skyrockets exponentially. Generating that massive localized pressure is necessary to cross a specific threshold, known as the critical fracture energy. That is the exact amount of mechanical work required to rupture a soft solid and create a new surface. This diagram models that transition. In panel A, the blunt tip indents the material, storing elastic energy. In panel B, once the fracture energy threshold is breached, the structure gives way. The material fractures, creating a deep crack for the metal to slide inside. By mathematically minimizing the surface area of the point, that critical fracture energy is exceeded almost instantly. The tissue ruptures with practically zero physical effort required from the angler. But shrinking the area is only half the equation. We still have to account for the F, force. And simply applying tension to a fishing line does not guarantee that force is directed into the target. When under tension, a hook's behavior is dictated by three geometric variables: the direction of pull, the hook's pivot fulcrum, and the point to fulcrum angle. In a standard J hook, the angled point splits the pulling force into two vectors, a forward axial force and a perpendicular transverse force. This transverse vector wastes energy. It creates a bending moment, pushing outward. Hitting a rigid jawbone, this lateral stress buckles the metal. Unless the point to fulcrum angle is geometrically aligned, generating massive pulling force won't pierce the biological armor. It will only destroy the hook. The structural solution to this bending moment is found in specific circle hooks or perfectly aligned inline rigs paired with chemically sharpened points. These shapes are engineered to achieve a 0-degree point to fulcrum angle. The sharp point is oriented completely parallel to the incoming line of tension. This geometry eliminates the transverse vector entirely. 100% of the line tension translates into pure linear compressive force. Under this pure axial load, the micropoint ruptures the critical fracture energy threshold. It slides deep into the cartilage with zero lateral flex. There is no violent scraping, no buckling steel, and no chaotic deflection bouncing off the outer scales. A secure hook set is the end result of metal and geometry finally aligning with the physics of the strike.